This is part 2 of the chapter 13 lecture. In this video, I'm going to discuss a heating curve and I'll qualitatively describe it, like what's the information we get from it by just looking at it. And then we're also going to do a calculation, which would be a quantitative type observation, and we're going to calculate how much energy it takes to change the temperature of a substance as well as to melt and vaporize that substance. So that's the two main components of this portion of the chapter 13 lecture. So let's start by talking about the heating curve. And this heating curve that I have here is for water. Excuse me. And you'll notice on the x-axis, it talks about the amount of heat added. So this is like setting something on a hot plate, and then you're going to add heat to, in this case, the water. And then we are looking at how the temperature changes as we add the heat. Now, for every heating curve, there'll be two plateaus. And I looked up the word plateau, and I want to set it here. Pulled it out of my pictures, and let me set it in. Okay, there it is. So a plateau, and you can see there on number 2, a state of little or no change following a period of activity or progress. So the plateaus in this diagram are the flat places. And these flat places occur at two important temperatures. The first one is at 0 degrees Celsius, which for water, that's going to be the melting point. And we talked about in the previous video that melting point and freezing point are the same temperature. I would refer to this as the melting point because I am heating it up. So when I get to 0 degrees in this situation, because I'm adding heat, it will start to melt from a solid to a liquid. You can draw cooling curves, which would start at a high temperature and you'd be removing heat. So in that case, I suppose we would call it the freezing point. But here we'll call it the melting point because we're adding heat, and it would be 0 degrees Celsius for water. And then the other important temperature is up here where the other plateau is, and that's at 100 degrees Celsius, and that is the boiling point of water. Or at least the normal boiling point, which if you watched the first video, you know that boiling point can vary with atmospheric pressure. So we're referring to the normal boiling point where the atmospheric pressure is 1 atmosphere. So let's talk about this then. The line represents, it's a pink and purple line. It represents how the temperature would change as we add heat, in this case, to ice. So we start, if you notice, and I'm going to use a bright color so you can see on the diagram, we start below 0 there at A, and this would just be solid ice. So we have a piece of ice that's below 0, so it would just be a solid. So imagine in a beaker, we just placed a piece of ice on a hot plate. And so as we add heat to that, the ice starts to warm up. Now, once it gets to 0, it's going to start melting. And the important thing to consider here is as long as there are two states, in that case are two phases, in this it would be solid and liquid, two phases present, the temperature remains the same, and that creates the plateau. So if I was to think about it, I would know that right where B is, that would be solid. And as I continue to add heat, if you imagine an ice cube melting, it creates a puddle first, and then eventually all the solid goes to a liquid. And so by the time we got to C, it would be a liquid. And in between B and C, there would be both things present. So one thing to remember is at these plateaus, what it's telling us is as long as two phases of the substance are present together, the temperature does not change when you add heat. Once the phase change is complete, so for example, the solid has completely changed to a liquid, then as we add heat, the temperature will start to increase again. So between C and D, what it shows is an increase in temperature as we add heat. And this point, it's all liquid. So in my imagination, this is where we have the water, we have it on the hot plate. You could even have a thermometer in it, and you're adding heat, and we just are watching the temperature go up. Now, eventually, when you get to point D, then it's going to start to boil at 100 degrees, and it will change from the liquid phase to the vapor phase, and we get this second flat line, and I'll tell you what that little up and down is in just a minute. So we have a second flat line, and this flat line at letter D, we start as a liquid. And then as we progress across, it's not until letter E where it can start to rise, the temperature can start to rise again, where it's a vapor, and everything in between has both liquid and vapor present. So again, as long as you have two phases present, the liquid and the vapor in the second situation, the temperature is going to maintain at that 100 degrees until the phase would be completely vapor, and then the vapor will finally start to rise again, which is here at the last part of the graph. Now, two things I want to talk about in the second plateau. One is this little up and down space right here that goes up and down. There's not really a variation in temperature. What it tells me is, in this particular graph, this second line actually could be way out here. Like if I were to do it to scale, it would be so much longer. But I don't have space in the graph I'm trying to draw to have that long line. So it's almost like they're taking it and pushing the line together, and to tell you that, they do the little up and down. So it's like it kind of folded. It's kind of that's how I would think of it, as like a little fold in the line. And what it's telling us is that really the line should be longer in proportion to the other lines. The second thing, so that's one thing, that little up and down is not a change in temperature. Okay, the temperature should be constant. The second thing I always think of practically is if you have to boil water for something at your home, maybe you're cooking pasta or something else, just know that once it starts boiling, that temperature will be maintained throughout the boiling process as long as there's still water present. And so it's not really helpful to let water boil for 10 minutes before you want to use it. Once it's boiling, that's as hot of a temperature as you're going to have. So this is our heating curve, and a few takeaways from this as you try to figure out, what am I need to know, what am I sure to understand. So you need to be able to label the different sections. You need to know that what it's watching is how the temperature changes in the y-axis when you add heat. Then know that the plateaus, or those flat areas, correspond to the melting point, which would be the first one on the heating curve, and the boiling point, which is the second plateau. And the especially important thing to know here is that for a system, the temperature will not change when you're adding heat as long as two phases are present. So the temperature will not change until you have one phase. Now the reason is, even though you're adding energy by adding heat, the temperature is not changing because all the energy is going into the melting or to the vaporizing of the substance. And it takes extra energy to melt and vaporize things and to change its temperature. So that brings me to the part that involve calculations. So in chapter 4, we learned that the heat required to change the temperature of a substance is equal to the mass of that sample times the specific heat, which is a constant, times the change in temperature. So that's T2 minus T1. And the way it was written is in abbreviations. It looked like that. I just wrote it out in words. So this one tells us what we need to change temperature. Okay, so that's the first equation. Then what we're learning new in this chapter is that it takes extra energy to melt and vaporize a substance. So to melt something, there's a second heat. So this is in this chapter. And this, you take the mass of your sample and multiply it by a constant called the heat of fusion. So that amount of energy is required to melt the substance. Now the heat of fusion, you can see it up here in the notes. It's the energy required to change 1 gram of a solid at its melting point to a liquid. So it's the amount of energy it takes to melt something. It is a constant, so it's not something we have to memorize. And then finally in chapter 13, we're also going to learn about a new amount of heat. This is the heat required to vaporize something, and that's calculated by taking the mass times the heat of vaporization. And you can see up above at the upper left hand of this screen, the heat of vaporization is just the energy required to change from a liquid to a vapor. So depending on the description of our problem, we might have as many as 3 different heats that we need to add together. Okay, so before I leave this page and do the problem, I'm just going to highlight things that are constants. So the specific heat is a constant. The heat of fusion is a constant, and the heat of vaporization is a constant. So those 3 numbers are given to us in the problem, or if they're not in the problem and we have a textbook, or if it was an exam, it could be on the exam sheet. We wouldn't have to memorize them. So the other things that they'll give us is the mass. You can see they'll give us the mass and the change in temperature if we're changing temperature. Now, not every question is going to require all 3 of these heats, although the example I'm doing does. You have to read the problems carefully because maybe it's only asking you to change the temperature. Then you would only use the first equation. Maybe it's asking you to melt something. Then you would just use the second, or vaporize. Or maybe you have to melt it and change the temperature. Then you would need to calculate 2 heats and add them together. So let's take a look at a problem. We'll see how when we read it, we can figure out which equations we're going to need to use. You might pause it right here and write down these 3 equations and be sure you note to yourself what they're used for. So the first equation is used to change the temperature. The second one is to melt your substance, and the third one is to vaporize it. So here's my practice problem, and I'm going to write down what they've already given me to start. So it says, how many joules of energy are needed to change 10 grams of ice? Okay, so there's my mass. ice is a solid, so I'm starting at a solid. And this ice is at 0 degrees Celsius. That's where I'm starting. To steam, which is a vapor, at 100 degrees Celsius. That's my T2. So I see I do know a change in temperature that I'm going to have. So I'm going to end up at 100, and I'm going to start at 0, so that would be 100 degrees Celsius is my change in temperature. I know the mass is 10 grams. And I know I'm starting at a solid and I'm ending at a vapor. And I know some things go directly from a solid to a vapor through sublimation, but I don't think it's talking about ice and steam. And so I think we're going to have to take a stop at the liquid. So we're going to melt it and go from a solid to a liquid, and then we're going to go vaporize it and go from a liquid to a vapor. So let's see what we would need to do. So first let's change the temperature, and the order doesn't really matter because you're going to add up everything. So this is heat equals mass times specific heat, which I'm just going to write as SH, times change in temperature. So that equals 10 grams times the specific heat, which is given to me in the problem, times change in temperature, which I calculated over here. Now, if you're like me and like to see how the units cancel, a degree Celsius cancels here, grams cancels there, and you're left with joules, which makes sense because we're calculating heat. So the first heat, the heat to change the temperature, is going to be, I have my calculator, 10 times 4.184 times 100. And I get 4,184 joules. So I'm going to call this heat 1. That's the first one I calculated. Now that just changes the temperature, but I start at ice and then I have to go to steam. So to do that, I'm going to have to melt it. And the heat to melt is the mass times the heat of fusion, which is a constant. So the mass for the whole problem is 10 grams, and the heat of fusion is given to me, it's up here, 335. Again, if you're thinking about canceling units, this gram cancels with that one, and I am left with joules, which makes sense for heat. So this equals 3350 joules. So my second heat is 3350 joules. So in this problem, if it didn't say to steam, it just said it changed the temperature to 100, then I wouldn't have to vaporize it, and I would just add these two together. So as you read the problem, you have to think to yourself, am I changing the temperature? And if you are, you would use equation 1. Then you also have to think, am I melting it or vaporizing it? And if you are, you have to add in those temperatures. So this problem, I have a third heat, and this is to vaporize. And that is that heat equals mass times the heat of vaporization, which is a constant. The mass for the whole problem is 10 grams, and the heat of vaporization is 2259. Look how much greater the temperature is to vaporize it than to melt it. I always think of it because when you melt it, you're just kind of loosening up the molecules. You're giving them enough energy so they can flow. But when you vaporize something, you have to give enough energy that the substance will completely come away from the liquid and go into the gas phase. So it takes a lot more energy. Again, going back to our problem, if the units cancel, then we're left with joules. All right, so then to solve this, and I'm going to write it up at the top because I've kind of gotten myself into a jam down here. I have 3 amounts of heat, and so the total is going to equal heat 1 plus heat 2 plus heat 3. So that equals heat, and the order wouldn't matter. There's heat 1 plus heat 2 plus the third heat. All right, so let me add those together. And I get 30124 joules. So that's the amount of heat it would need to change 10 grams of ice at 0 to steam at 100 degrees. Now, if I'm thinking of significant figures, I feel like 3 significant figures, just looking at what I was given. I see that I have the 10 grams, that's 3. The temperature change is 4 significant figures. The heat of fusion has only 3, this has 4, and this has 4. So I feel like 3 would be appropriate. So I could either write 30100 joules or 3.01 times 10 to the 4th joules. That would be my final answer. So what you need to remember for these problems is there's 3 different equations. All of them involve a constant which would be given to you, or in your homework you might have to look it up in the textbook. And so read the problem and figure out which heats you need to utilize. Is it changing temperature? Is it melting? Is it vaporizing? So figure out which ones and then add those together and you'll get the answer. So go and practice your problem, or look at some of the sample practice your homework, or look at some of the sample problems. And if you run into trouble, let me know and we'll figure it out.